All right, so this is lecture number 16 for distributed energy resources. The last three lectures, we talked about optimization. So we kind of introduced optimization broadly as a field. Then we talked about convexity as kind of a way to simplify the very large and challenging landscape of optimization. And then last lecture, we talked a little bit about basically how we solve convex optimization problems in practice. And so that was kind of a two-part lecture. In the first part, we talked about how to use modeling languages that basically take the sort of problem specification that we can write down on paper and then map it into the very technical specification that gets sent to a solver. And then they go and solve the problem, bring back the solution, and kind of reframe it in the way that you had originally posed it. So that was part one, was learning about these modeling tools. And then part two was looking at sort of under the hood, what might be happening with the optimization solvers. And so there we talked about several kind of classic and fairly widely used methods for optimization. We talked about gradient descent. We talked about Newton's method. And then we talked about barrier methods, which are methods for constrained optimization, more or less generalizations of Newton's method to constrained optimization problems. And then that built up finally to interior point methods, which is really basically what's happening under the hood with most of the solvers that the modeling languages we'll use in this class interact with. Okay, and then, so this is kind of eat your vegetables again, right? So we had some eat your vegetables portions before the first unit on simulation, right? We basically had a couple of classes that were basically just math classes about how to model and simulate ordinary differential equations. And then we had three more lectures that were basically a math class about how to do optimization and convex optimization specifically. So now we will get back for the last 4 or 5 lectures of the semester, we will get back to DER applications. So today in this class, we will talk about the sort of objectives that often show up when we are solving DER optimization problems, whether they be how to design a physical system or maybe how to control a system once it's out there in the world. So we'll talk about the different, minimizing emissions, minimizing energy costs, minimizing peak demand, things like that. And then next lecture, we'll talk about batteries specifically, and I'll show some optimization results to give a flavor for what happens when you optimize batteries. And you may remember that a lot of the DERs that we studied, we kind of showed that they could be more or less reframed as battery-like models. So they could be modeled sort of as a thermal battery, if we're talking about a building or a water heater, for example. So in some sense, once we learn how to optimize batteries, we sort of have learned how to optimize a whole bunch of other DERs as well. Lecture 18 here, we'll talk about regression. This is basically a machine learning type problem. You have some data, continuous valued rather than discrete, say integer valued, something like that. Features or outputs that you're trying to train a model based on data to predict. And so that comes up in a couple of contexts for DERs. One, it might come up with load forecasting. So if you're a utility, for example, and you want to understand what your demand is going to be from your service area tomorrow at 4 p.m., you might want to use a regression model that takes input data related to weather, time of day, things like that, and produces outputs that might be the energy consumption of a community. So that's one context when regression comes up for DER applications. Another is basically trying to fit the parameters that go into some of the models that we learned about. So if you are modeling a building, for example, we talked about RC or 1R, 1C type models for buildings. But what should the values of those parameters be? What should the R be? What should the C be? How do we come up with those? And so we'll talk about some ways to use data and regression methods to come up with that. By the way, all the regression stuff that we will do here will use convex optimization. So it's basically a special case of what we've talked about here already. And then in the last lecture here, we'll get to, you could call this optimal control or optimization under uncertainty. But most of the stuff we do before this lecture 19 will assume more or less that we have complete information or perfect information about the system that we're trying to work with. But what if that's not the case? So what if you have imperfect predictions, for example, of the power that will come off of a solar array? How do you take into account that uncertainty when you're trying to make decisions about that system? The last couple of lectures here are a little bit up in the air. One of them, we will take a tour of a facility, actually a research facility that I'm involved with near campus. It's basically a test house that has a lot of the DERs that we've discussed in this class. I wanted to take you guys on a tour of the Wade utility plant, the power plant that serves Purdue's campus. But unfortunately, it's under construction right now, so they're not doing physical tours. Sorry about that. In a future semester of this class, I will do that again, and maybe I can add you guys to the mailing list, and you can tag along if you would like to. Also, in a future semester, I would like to go to MISO, the Mid-Continent Independent System Operator, which is one of the big kind of transmission grid operators, one of 7-ish in the country. And they're headquartered about 45-minute drive from here in Carmel, Indiana. And so not this semester, but probably next year, I'd like to lead a trip. So if you guys want to do that, shoot me an email and I'll try to involve you in that. And that's it. And then the last 4 lectures of the class here, basically a couple of weeks from April to early May, you guys will be presenting your final projects. And so that's really the work that you guys should be doing in this period from spring break to final exams, basically. I'm only going to give you one homework assignment. And so each week you should be spending significant hours working with your teammates and plugging away on your problems that you have chosen. So any logistics questions before we dig into lecture? Yes.
Will the DC house be recorded anyway, or wrong?
Oh, yeah. So what about online students for the DC house tour? I mean, we could do something low tech, like walk around with a cell phone pointed at stuff. I'll have to think through that. That's actually a really good question. Do you have any suggestions?
Log on Zoom.
Yeah, make a video, put it on Brightspace, something like that. Okay, we can try that. Other questions? Okay. All right, so again, today we're going to take some of the kind of really abstract information that we learned over the last few lectures about convex optimization, and we're going to start applying it to DER optimization problems. And so today we're just going to begin by running through basically like, what is the point? What might we want to do if we had control over a bunch of DERs? So we'll start by just giving a recap of electricity economics. So some of this will be stuff that we talked about in lecture 2 or 3, but some of it will be a little bit new as well. And then I'll give some reminders about optimization stuff, things that we learned that are now ancient history, stuff from before spring break and so on. And then basically go through a bunch of example objectives and then end up with an example here. Okay, so you may remember week 1 or 2 of this class, we talked about the sort of utility business model and the regulatory model that electric utilities face. And we talked about a couple of different versions of that you can find here in the US and in other countries more broadly. And one of them is the vertically integrated model. And this roughly was the model that was used in the US from the early, late 1800s, early 1900s, all the way through about the year 2000 or the mid 1990s at least. And so the idea here is that almost the entire stack from electricity generation, so this is power plants, transmission, so this is high voltage power lines, distribution, so these are the lower voltage kind of or medium voltage, you might say, power lines that you would see if you walk around West Lafayette, for example, and then load. So this is how electricity is used. And so other than the load, which is typically under control of a user, there's basically one entity that controls the generation, transmission, and distribution assets in this vertically integrated model. So we have electricity flowing kind of from the center outward to the edge, and we have money flowing from people back to the utility. And then there's an information exchange between the utility and the state regulator, which is either appointed by a governor in about 10 states or elected in about 10 states or appointed by governors in about 40 states. And basically, the regulator says yes or no to stuff that the utility might want to do. So utility classically would say, we want to raise electricity prices for this class of customers from this rate to some higher rate in order to pay off some infrastructure that we had to build out. And the regulator might say yes or no, or yes, but you want to raise prices by 10%, but we're only going to let you do it by 5% or something like this. Okay, so that is one model. Another model that you might call deregulated or liberalized or competitive wholesale electricity markets basically broke up that vertical stack. So rather than just having one entity, the regulated monopoly utility who controls all three of these levels, typically you would have one utility controlling the distribution, the sort of medium voltage poles and wires and transformers. And then there might be a separate owner who owns transmission, and typically, these are not allowed to be the same company. So the distribution and the transmission grids are separate in ownership. And then there might be a third company who owns the generation, or in some cases, you might have a distribution utility also owning generation. So they can be, two companies rather than three, basically. And then there is a nonprofit called either an independent system operator or a regional transmission operator, ISO, RTO, or a TSO more generally. I guess that's the term that integrates both of those, a transmission system operator. But they basically coordinate the system in order to promote or maintain reliability of electricity supply. But they also provide basically a market platform where the people who want to sell power, the generation owners, and the people who want to buy power, the utilities who serve ultimately the end users, can basically interact and submit offers and bids and have a market that clears and pays people money kind of in proportion to the services that they provide. Okay, so today, most of the US now has deregulated electricity markets. So most of the US is now covered by ISOs and TSOs. So in the Northeast, we have ISO New England. By the way, in theory, ISO, independent system operator, is a grid operator, a wholesale or transmission grid operator that only covers one state. So if you look at like the Wikipedia definition of ISO versus RTO, regional transmission organization, that would be the delineation. Does it serve one state or multiple states? However, that same nomenclature is not really used by the ISOs and RTOs themselves. So ISO New England calls itself an ISO, for example, but it actually covers multiple states, 5 or 6 states in the Northeast. New York really does only cover one state. California, roughly the same. The Texas grid operator, only one state as well. And then all of the others cover multiple service areas. And then the Southeast here and some of the West is still kind of in the regulated, vertically integrated utility model. And this is changing. This map is a little bit out of date actually today, probably, because even in the last 6 months or year, some of these boundaries change and things like that. So here's a comparison of the wholesale price of electricity, which is kind of the bulk sale of electricity that happens from big generators, such as a nuclear power plant, for example, which might be a gigawatt scale facility. When they sell a bunch of power to like the entire utility that serves me and all the neighbors in this area, Duke Energy, right? So Duke might buy from a nuclear power plant as one example. So the wholesale market covers many of those transactions. There are direct transactions actually, which where people can circumvent the market, where a retailer like Duke Energy and a nuclear power plant, for example, could just make a direct contract and say, we commit to buying and selling power at this certain price and this certain amount for the next 5 years or something like that. And actually power providers like that, and actually I think power generators like that as well, because they can sort of hedge to some extent against the risk of price volatility in the future. So you might want to lock in at a okay price, some amount of demand, rather than being exposed to what might be a really good price or it might potentially be a really terrible price. So usually people who buy power have a mix of these kind of forward contracts that they lock in at a fixed price versus buying some excess on the wholesale market. Anyway, so this is 2010 through 2018. And then the y-axis here is the price of electricity in cents per kilowatt hour. The yellow curve here is the wholesale price, and this is just for one of the ISOs, ISO New England. And then the top here, the dark blue curve, is the retail price of electricity. So this is roughly what you or I would pay. I think here in Indiana, I pay about 14 or 15 cents per kilowatt hour. So this is roughly current electricity prices. So you can see one thing here is that there's roughly an order of magnitude difference between the wholesale price, which might be on average maybe 3 or 4 cents per kilowatt hour, and the retail price, which might be about 5x that at about 15 cents a kilowatt hour. So that's one trend. Do you guys notice any other trends from this graph? Yeah, there's a lot more volatility in the wholesale price. So we see big spikes here. But the retail price, it reflects those spikes a little bit. But there's much more sort of attenuation or damping of the volatility, right? And so that's one function that something a company like Duke Energy, for example, provides is they're exposed to the volatility from prices, and they kind of absorb that and pass on a more constant, a more predictable price to end users, which is potentially valuable. Um, and then I guess so the light blue versus the dark blue here. So the energy component, this is basically what someone like Duke Energy would be paying for the energy that they buy, either via direct kind of forward contracts or off of the market. And then the light blue component of the price, roughly half of the retail price, basically is them taking their infrastructure costs, the costs that they incur by either buying or maintaining and operating all the power lines and transformers and capacitors and switchgear and all that kind of stuff that goes into a distribution grid. And so they basically take the cost of all of that stuff and they roll it in to the energy price that we pay, roughly. Okay, and then that price that gets passed on to consumers is different depending on the type of consumer. Yes, question.
Spikes occurred in the wholesale, like,
Why did these spikes occur in the wholesale? I have a guess. Does anybody else have a guess? Is it the end of a contract with a generation company? No, I don't think so. Oscar?
I think some kind of outage or some large scale event.
Yeah, something like a power outage or a large scale event. That certainly can happen. So if you remember back to, we talked about how these markets clear and how they set the prices. We talked about what's called the merit order, where you basically stack up generation offers from the cheapest to the most expensive. And as demand goes up and up and up and up and up, you get higher and higher in that stack. And so the price of electricity goes up and up. So when the grid is really tight, meaning demand is almost at the capacity of supply, then you can get really big price spikes. Yes, Jennifer? Was it Hurricane Sandy? That might have been in the 2015-16 era. It could be. But so roughly, uh, okay, basically weather extremes are one reason that we see price spikes. So if air conditioning demand goes through the roof on a really hot afternoon, that's one reason why supply and demand might be really, really tight. Demand might be like as high as you can accommodate in a grid. Another reason would be oftentimes, if you remember the marginal pricing scheme, basically the last generator in that stack of generators to get dispatched is the one that sets the price for everyone across the board. And so if that marginal generator has a really high cost of fuel, so for example, it's not shown on this graph, but when Russia invaded Ukraine, global natural gas prices went through the roof because Russia is a major natural gas supplier to Europe and Asia as well. So the global price went through the roof. The prices that we pay here in the US are linked to global prices because the same companies that supply natural gas to power plants here in the United States have an option to instead supply that natural gas overseas to Asian markets or European markets, something like that, by basically compressing it and refrigerating it and shipping it in big tankers. So when prices go up or go crazy on global markets, they oftentimes go up in domestic markets as well. And then those natural gas fired power plants get really, really expensive to run. And that drives up basically the price for electricity for everyone because they're very often the marginal generators. Yeah, Oscar.
If we extended this graph over to, 2025,
Yeah.
would there be some amount of decrease due to like wind or renewables in the Northeast, or would it be pretty similar?
So the question is, if we extended this forward into times when there's more renewables on the grid, would we see either the wholesale price or the retail price going down to reflect this low cost generation? Maybe at the wholesale level. I think there's a mild downward trend in some wholesale markets reflecting low marginal cost resources like wind and solar. On the retail side, this price almost never goes down in a sustained way. So there's a little bit of a dip here for several years, but basically the trend is more or less up and up and up forever.
Just as
And
prices rise.
prices rise, the cost of maintaining and operating grids goes up.
That blue line is very steadily climbing.
Yeah, this blue line is going up. It certainly doesn't go down in a sustained fashion very much, right? And there are maybe political and regulatory reasons why that might be the case as well. So again, the basic structure is utilities want to raise prices. They go to the regulator and they say, can I do it? And the regulator says yes or no. We talked about what's called regulatory capture early on in the semester, where the people who regulate, who get appointed by governments to regulate utilities, well, I'm not saying that they necessarily are corrupt or anything like that, but just there are, we'll say, political forces or lobbying forces or things like that that often make it so that the decisions from those people are quite friendly to the businesses that they regulate, basically. So if we also just structurally, if a utility never goes to their regulator and says, can I reduce prices?
Yeah.
Then the regulator, I guess in some places they could go to the utility and say, you must reduce prices by 10%, but very rarely does that happen, at least in my experience in practice.
Stuff you can't not buy electric. I mean, you could not buy, but you're kind of, it's an essential good.
It's kind of a captive market, right? Like people, yeah, I mean, there's some discretionary aspect of electricity use, but a lot of it is really necessary. Yeah. Yes.
All of those spikes occur in winter. If you look at it in the early 2014, early 2015.
And maybe it's heating.
So yeah,
I guess
it's like a
and
really
really
cold
cold maybe.
winter.
Yeah, so one of these is probably a polar vortex
Yeah,
event, right?
2014, I think was the big next
Yeah, yeah.
It could be that. Man. Because
Yeah, it could be that a lot of people were running electric heat during a cold snap. Yep, that could be part of it too. All right. So anyway, that's kind of the difference between wholesale and retail prices. And again, that's just like, what would Walmart pay for Coca-Cola versus what do we pay Walmart for Coca-Cola? That's the difference between wholesale and retail, essentially. But even within retail customers, there can be different pricing. So if I don't know, if a catering company wants to go to Walmart and buy a whole bunch of Coca-Cola, Walmart might give them a bulk discount, for example. So industrial customers, so this is basically manufacturing and things like that, chemical processing, other heavy industry stuff, typically get a significantly lower price for electricity than what residential customers, people like you and I, pay in our apartments and homes. And in between typically is commercial. So this is things like office buildings, schools, hospitals, and so forth.
that virtually doesn't work. Maintain, like, we're going to process steel, we need megawatt day.
Yeah. So the question is that partly because the load from industrial customers is sort of more predictable and stable and things like that? That could be part of it. Yeah. It's a complicated thing, and I don't know the full history. And I imagine, like most complicated questions, the answer is it depends, and there are lots of factors.
Is there also some idea that maybe if you're a energy provider and you have some industrial people who want a megawatt every day, that if you don't give them a competitive price, they could just say, okay, we're going to generate electricity on our own. We'll buy natural gas and burn it for the plant here.
Yeah. So part of it, just to paraphrase that a little bit, is that industrial customers might present sort of a credible threat that if the prices are too high, look, I'll just go buy my own generator and do it locally, right? Where it's much harder for a retail customer, a residential customer rather, to do that. It's getting easier with solar panels and battery prices and things like that coming down, but yeah, I think that might be part of it as well. Yes.
Is it, well, I mean, I guess also the partially distribution, right? Like you're delivering a lot of power, but it's all going to one spot.
Right. So so the comment is here, if you think about the price that retail customers pay, it's about half delivery charges, which has to do with just the equipment, the infrastructure, the power lines and things like that. So if I'm a residential customer, there might be thousands of customers like me, each of whom needs a line going from a transformer down to our house, a drop. Whereas if you have a utility who consumes as much power as 1,000 households, you basically just need one fat wire going to that industrial facility rather than 1,000 little wires. So yeah, there are some economies of scale, I guess, in that sense, and that may be part of the reason for this. Anyway, for whatever reason, industrial customers often pay significantly lower than commercial, who pay significantly lower than residential. Okay, so that's kind of the fun background. We'll go into a little bit of math, and then I'll start showing some pictures here. But just to prepare you guys for like what's gonna come in the pictures and the pricing and stuff, we want to talk a little bit, just some reminders about what we learned about optimization. So one important object that we learned about is an affine function, which is basically a y equals mx plus b type function, but potentially in higher dimensions. So a function here, and I'm talking about scalar valued functions, but you can generalize this to vector valued functions as well. But f here, going from Rn to R, is linear if it can be written as basically ax, the inner product of a and the vector variable x, for some vector a. And then we call it affine if it's linear basically plus an offset. So if we have, again, a scalar b that we add to the affine, or the linear function here. So all linear functions are affine. Basically, if you take b equal to 0, then these two functions look exactly the same, but not all affine functions are linear, right? And then we also learned that a function that is both convex and concave is an affine function, and the converse is also true. And then we talked about curvature. So when is an affine function a non-decreasing function? Well, one way to test with a continuous function to test if it's decreasing or increasing is to take the derivative, and then the sign of the derivative tells you if the thing is sloping up or sloping down. So if we differentiate f of x here with respect to, say, x1, the first component of the vector x, we would just get a1. The b drops out, and we just have the thing that's multiplying x1. So if ai is non-negative, then we get that the function f is non-decreasing in that argument xi. And then finally, minimizing an affine function is equivalent to minimizing the linear function. So if we want to minimize ax plus b, well, b we can't affect by changing the decision variable x. So you might as well just minimize the component that you can control, the ax, right? Okay. Another reminder, we talked about composition rules for both curvature and monotonicity. And we talked about basically one good way to build up a library of interesting convex functions is to start with some really simple kind of atomic convex functions and then propagate them through transformations that you can certify maintain the convexity of those functions. And so we have some rules for how to do that. If we have a convex function of an affine function, that composition is convex. If we have a convex and non-decreasing function of a convex function, we again get a convex function. And then if we have a convex non-increasing function of a concave function, that composition is again convex. Yes.
Is the right way, like, is this essentially saying like f of g of x? Is that
Yeah.
okay?
Yes, that's right. So you can think of this as this is a shorthand that I'm just writing down here. The more mathematically rigorous way to do it would be to write down f of g of x. And then you'd say that composition, depending on the properties of f and of g, you get a convexity and monotonicity rule for the composition. There are analogous rules for concave functions, so stuff we can do that gives us a concave thing. And then we also had rules for monotonicity. So if you have a non-decreasing function of another non-decreasing function, the result is non-decreasing. And then non-increasing of non-increasing is again non-decreasing. And the other two combinations that you can imagine give you non-increasing functions. So the way I remember this is by saying, basically, if you compose with a non-increasing function, it essentially flips the monotonicity property. So non-increasing of non-decreasing, we flip that. And similarly, non-decreasing of non-increasing, well, that preserves it, right? So non-decreasing preserves the thing that's on the inside there. And for this one, we basically have, I don't know, two flips, I guess. Yeah, I think I walked through verbally this example, but I think people who are starting to learn this material often think like, oh, if I have two convex functions and I compose them together, the result should again be convex. But that's not actually true. We need something else. We need a monotonicity property as well. And so here's a counterexample to show that a convex function of a convex function is not necessarily convex. So suppose that we have g is just negative, g of y is negative y, and h of x is equal to x squared. So both of these are convex functions, right? Because this one is linear, hence affine, hence both convex and concave. And this one over here is a convex function. But if we take H and plug it into G and make the composition G of H of X. So call that thing a new function f of X. Well, that's negative x squared, and that looks like a hill, right? So that is a concave function. And so in order to get the sort of composition rule to do what we want, to preserve convexity, we need the outer function, in this case, the function G. We need that thing to be non-decreasing in addition to being convex. Okay, and then going back, we had a summary lecture for DER modeling, where we went back and we reviewed the models that we developed for all the different kinds of thermal storage for 1R1C and 2R2C type models of buildings, for batteries, for electric vehicles, and so on. And we more or less cast them all into one sort of general framework that basically captured the dynamics and the constraints that we see with all of those DERs. And so here, X, you can think of as a state variable. So this could be an energy stored in a battery. It could be the amount of heat stored in a water heater. It could be the amount of heat or cooling stored in the thermal mass of a building, something like that. Then we have constraints on that. These could be related to comfort constraints in a building. They could be related just to the capacity of a battery, something like that. We also have constraints on the action here, U, the thing that we can do, the energy that we can squirt into a battery, or the air conditioning that we can extract from a building, something like that. And then we have this disturbance term W, which is basically the things that affect the model that we can't control. So this might include the outdoor temperature. It might include sunlight. It might include driving patterns for an electric vehicle, things like that. Anyway, we have, again, linear constraints on the actions that we can take. And then we have a function here, P, an output here, P, which is basically the electric power that we exchange with the grid. Typically, we defined it to be positive if we're pulling power from the grid, for example, to charge an EV, and negative if we are pushing power back to the grid, for example, by discharging a battery. And so P is some function G, which could be nonlinear in general. And it can, in general, depend on both the state variable X as well as the action variable U. And then the parameters A and B here are scalars. And they come from things like the time constant, the self-dissipation time constant of the battery, or the thermal resistance between the indoor and the outdoor air, stuff like that. Okay, and then this particular function G was an affine function for some of our DERs. And for other DERs, it was a nonlinear, a non-affine function, a convex function. And it had different sort of monotonicity type properties depending on the system that we're talking about. Okay, so with that model in mind, and again, remembering that this thing can model like 6 or 7 DERs that we studied in the first half of this class, a fairly general problem for optimizing the operation of a DER. We'll talk about design problems a little later. But for operational problems is to basically choose the state, the whole trajectory of the state over some time span. We could be looking ahead a day at 5-minute time steps, for example, in which case this capital K would be, I don't know, 12 times 24, whatever that is. We also want to optimize the actions that we take. And then the outputs, P here, that result from the actions and the state trajectories, this would basically be the power profile over the course of the day that we exchange with the power grid. Typically, this is not perfectly general, but very often the objectives are really a function of that power trajectory. So we want to shape that power profile. And we can do that for various reasons. But that gives us some function of the P trajectory. And then we have some constraints. So often we will know the initial state of our system. So we might know what the temperature in the building was at the beginning of the day, or how much energy was in the electric vehicle when someone came home from work. We have the dynamics, and then we have our state and our action constraints. And we also have this function, the output function that describes the electric power. And then we have a bunch of information that we're given, the initial state, the dynamics parameters generally, all the upper bounds and lower bounds on the constraints, as well as some predictions or forecasts of the disturbance terms, the W's that show up in our equations. Okay, so then as we look through the objectives, the things that might show up in the objective function up here in our optimization problem, we'll want to pay attention to basically the composition of that function, whether it's the function that gives us the energy cost or the function that gives us the peak demand, something like that. What happens when we compose that function with g down here, the function that gives us the power in terms of the state and the action variables? So if this function g is affine, which is the case for some but not all of our DERs, then all we really care about is that the function of power, the g function here, or sorry, the objective function here is convex. That's kind of all we need. We don't need to think about monotonicity. But in some cases, this function here, g, is a convex function. And in that case, we want the function that gives us the objective to be not only convex, but also non-decreasing, so that we get convexity of the overall optimization problem. Questions about that? All right, so that was just some background. So let's dig in then to some objectives, and I'll show you some pictures of how to visualize some of these things. So probably the simplest would just be we want to minimize the energy use from our device. So this would be an energy efficiency problem. So suppose to do that, basically we would just integrate our power profile. And the simple way to do that is to assume that it's kind of constant within each time step. So we just multiply it by our time step and then add it up over the whole horizon. Alternatively, we might say, well, we don't care about the energy exactly. Energy is interesting, but it's almost always just a stand-in for something else that we care about, like emissions or money or other air pollution, something like that. So we might specify a price of electricity. It could be low at some times and high at other times. And this would give us the sort of instantaneous cost of electrical energy. But then we'd integrate that and get the cost over the whole day. So here pi e would be our electricity price. Okay, so this thing is linear in P and non-decreasing as well, because generally speaking, we talked about monotonicity of affine functions. You basically just look at the sign of the multiplier, the A vector. And so here we're just multiplying by delta t. That thing is always positive. Here we'd have delta t times the price, which in general could be positive or negative. And there are situations in which you might see a negative price of electricity, which basically means the utility would pay you to use electricity. So one example of where that might happen would be in Texas, for example, where there is a ton of wind power on a warm or a sort of mild, say, spring or fall night. Wind typically picks up at night. Demand typically drops off at night. And so you might have cases where there's actually more wind in the Texas grid than there is demand for electricity. And so then all those power producers prefer not to turn off all their wind turbines and stuff. So they might say, hey, we'll give you a little bit of money to basically soak up all that excess wind. Okay, so if that happens, then we'd get a negative price. And then this function of P, this affine function of P that gives either the energy, or sorry, that gives the energy cost, would be a non-increasing function rather than non-decreasing function, because the sign of the multiplier here would flip. Okay, so what does that look like? Here is just a constant electricity price at 15 cents a kilowatt hour. This is about what you and I pay for energy. This is what's called a time of use price scheme, where you have maybe a low price overnight and then a high price during kind of peak times for the grid, which at least today tend to be driven by air conditioning demand. And that typically peaks in the afternoon and early evening. And there are other versions of this where you could have not just 2 tiers, but you could have 3 or 4 or 5 different tiers that cover different times of day. They might vary from winter versus summer and things like that. And then, one detail here is that the area, these rates are typically designed such that the area under the curve, whether you're looking at the black curve, the kind of constant price, or you're looking at the blue curve, if you integrated these things and you looked at the area under the curve over a day, you would find that the areas are the same. So what that basically means is if you had a perfectly flat load, which in some sense is like the easiest load to meet, it's like super predictable, right? If you had a perfectly flat load, you would be neutral. You wouldn't care which of these price schemes you had, because you would pay the same amount of money to the utility either way. So they're typically designed with that principle in mind. And then there's something else called a critical peak pricing scheme, which might look kind of like a time of use price scheme, or it might look like just the dashed black line. And it might be even lower kind of in normal circumstances than the time of use rate. So it might be lower overnight and it might be lower during this peak period. But then on what's called a critical peak. So basically on a day when electrical infrastructure is super, super strained, maybe it's a heat wave and air conditioning demand is just going through the roof. We just talked about how wholesale prices, the price that a Duke Energy or a utility would face on the market, might go through the roof. And so they really want the demand they have to meet from all the buildings and stuff like that on their network to be low during those periods. So during an extreme critical peak pricing event, they basically would say, okay, it's these hours, say 2 p.m. to 6 p.m. That we really, really, really care about. And so a day or two in advance, maybe based on weather forecasts or something like that, they would give you notice. They would say, okay, I get 6 days like this per year, 6 critical days. And I'm letting you know that Saturday is going to be a critical day. And so I really, really want you not to use energy during this period. And so to encourage you not to use, they would basically send the price through the roof. So this is almost, I don't know, going up to maybe 70 cents a kilowatt hour, up from say 12. So that's a pretty significant 5x, 6x kind of increase. By the way, flat price here for electricity is super common. This is by far the most common residential rate. Time of use rates are usually available, but they're often on what's called an opt-in basis, meaning you have to look at your options from your utility and choose. I want to switch from the simple fixed price into a kind of a time varying price here. And then critical peak price is like even more rare. So I would say way less than 1% of retail electricity buyers probably have a critical peak price program. Yes, question.
I know that do we have more than that?
So the question is, what are the most relevant sort of time of use rate structures? Is it 2-tier? Is it 3-tier? Is there something else beyond that? It really varies. So rates actually vary a lot from one utility to the next. And even for a given utility like Duke, who serves maybe 10 different states. If you look at Duke, Indiana versus Duke, North Carolina, the rate structures might be quite different. Because they basically, again, they have to ask their state regulators, hey, I want to change something about my rate plan. And the regulator can say yes or no, or yes, but, and then they can provide some criticism and things like that. So for that reason, and this has been going on for 100 years. So for that reason, there's a lot of diversity in these things. But I would say most common time of use rate is probably a 2-tier time of use rate, where there's like a peak period and an off-peak period. And then there may be 3 tiers is somewhat less common, but not unheard of, where you'd have kind of an off-peak, a shoulder, and then a non-peak, or they might call it off-peak, peak, super peak, something like that. Yeah. Okay, this is actually a lie. This is not today's wholesale price from MISO. This is 1 year ago today, roughly. So I did not have time to update the slide from last year to this year. But this is fairly typical. So you'll note that the scale here is way lower. Here, the critical peak pricing went up to 75 cents a kilowatt hour. And here we're looking at 3 cents a kilowatt hour. And you can see the kind of the load profile has this sort of hump in the morning, lower in the afternoon, and then a big peak in the evening. And I think this is mainly driven by like people coming home from work and turning on the lights and turning up the air conditioning and cooking and doing all the stuff that we do kind of in the evening hours. And then it sort of tails off toward midnight there. And this is pretty common, sort of bimodal shape where you have kind of a hill, a valley, and another hill. Yes.
So this is for wholesale energy price. So is this being sold like to Duke Energy to the distributors? Is that the idea?
Yeah, so this would be like if you wanted to start a business that does what Duke Energy does,
Okay.
buy wholesale and sell retail.
Would you buy this energy if you were like a plant processing steel or something? Or is that like a different, like, oh, I'm going to buy from Duke Energy wholesale price? You couldn't buy straight from MISO, or you could?
Yeah, so who can buy from wholesale markets roughly is the question.
Yeah.
And it's not just utilities. They're the main customers, right? The people who do this retailing business. They buy wholesale, sell retail. But also, yeah, if you're a big industrial facility, rather than going through utility, you might say, look, I'll hook up to the transmission grid directly. I'll hook my factory up to the high voltage transmission grid, and I'll just buy what's coming off of the market directly.
Like if I wanted to set up, like in China, they have this place where you can go take your EV in and just get a battery hot swap. If I
Yeah.
wanted to set those up down the street,
Yeah.
I could buy energy from myself.
Yeah, so if you wanted to set up a fast charging station for EVs or a battery hot swap station for EVs, yes, it might be like you'd have to build some infrastructure
Yeah.
and you'd have to get some approvals for interconnection to the MISO grid and stuff like that. But if the laws permit it, it might be worthwhile because we saw that there's like often a factor of 5x difference between the retail price and the wholesale price. So you would much prefer to be able to buy wholesale. Yeah. And other, like an aluminum smelting plant that might use hundreds of megawatts of electric power to basically, take raw aluminum and turn it into sheets of aluminum that can be used for cans and stuff like that. They might, because they use so much electricity, it's such a big cost for them, they might invest millions up front to do that, so that they can buy wholesale rather than buying through their local utility. Good point. All right, so that was the first objective. I think there's no chance of getting through all these slides today, but that's okay. So another objective would be pollution or emissions, or you could come up with something like a dollar value of pollution or emissions. So there's lots of different types of emissions that we might care about. CO2, if we care about global warming, might be a big one. CH4, so this is methane, which is the main component of natural gas. We did some homework and problems where we talked about how methane emissions can actually be really significant when we're looking, for example, at space heating ecological footprint. And then there's some air pollutants that can have serious health effects to people who breathe them nearby. So that might be oxides of nitrogen or sulfur are two examples of that. So yeah, there basically it's similar to looking at something like the energy cost where we'd have a price, except rather than having a sort of dollar per kilowatt hour price, we might have a grams or kilograms, sorry, a dollar per gram or a dollar per kilogram price on the criterion pollutant that we're looking at here. So we'd look at the power we're using, we'd integrate it to turn it into energy, and then we'd multiply it by a pollutant intensity to get that. Alternatively, maybe you don't care about the mass of pollution that's being emitted. Maybe you care about something like a dollar value of that. Sorry, I think I misspoke up here. So this would be like a kilogram per kilowatt hour number. And then down here, we would have like a dollar per kilogram number. So we would multiply the pollutant intensity, which can be time varying in general, depending on what sort of power plants are producing electricity at any given time. And then we might multiply that with a price, and that price, I guess, again, could be time varying. On hot, muggy, humid afternoons, for example, air pollution tends to be worse than air pollution on kind of a windy, clear night, for example. If the air is sort of stagnant, the pollution can sit and do more harm to people's lungs and throats and hearts and stuff. Anyway, so this function similarly is always linear in P, and it's convex. Actually, it's non-decreasing if both the price and the pollutant intensity are non-negative. And in general, that would be the case. I don't know why you would ever say, I want to pay somebody to emit pollution. Okay, and then there's something you might call demand flexibility, and this is a little bit of a vague term, but here I'm defining it essentially as the capacity to adjust your power consumption, either upwards or potentially downwards, and not to just do it randomly, but to do it in response to something happening on the grid, some signal coming your way. So a grid operator today, or more likely in the future when grid operators get a little bit better at integrating DERs into their operations, but they basically can pay either for planning or reserving the capacity to adjust your electricity usage. So that would be like a capacity problem. Or they might actually call on you to use your flexibility. So in real time, they might say, look, you told me that you can, the 1,000 refrigerators that you're controlling, that you can decrease energy consumption from those fridges by 10 megawatts. And the grid is in crisis right now. I'm going to pay you to actually use that. So then you would send out a call and you would raise all the temperature set points in the fridges, for example. Anyway, so that would be a real-time or usage problem versus a kind of day ahead or a planning type problem. So if we want to plan a trajectory that reserves flexibility, we might get an objective related to flexibility in an optimization problem. And so here we could think of the upward flexibility as basically your ability to move from your sort of nominal consumption P up to a maximum consumption here. So this might be, the 5 kW at which you can charge a home battery. And then there's a downward flexibility as well, which basically says how far down can you ramp. And this might be 0. You could turn the equipment off completely, or you might say, I don't want to turn everyone's air conditioners off. or turn everyone's fridges off. I just want to let them kind of warm up a little bit. So you might say, yeah, I can drop it, but only by 20% or something. Okay. So the flexibilities here, the upward motion and the downward motion are both affine functions of the power P. And then upward flexibility is non-increasing, downward flexibility is non-decreasing. And then either way, if we multiply by a non-negative price, which is the norm, then, sorry, not norm in the sense of a function that measures distance, just the normal thing to do. There, generally, we preserve the monotonicity property as well. Okay, and then, so these are kind of atomic linear objectives, but we can put them together. We can add up a bunch of linear objectives, for example. We can have a mixture of, suppose we care about the dollar cost of electricity, but we also care about sort of the value of the pollution that gets emitted when the electricity is generated. So in that case, we could combine the sort of economic objective with the environmental or the public health objective. And basically, we get another linear function here. But we just have a different price, where this price is actually a mixture of the electricity price plus the pollutant price times the pollutant intensity. And this should look familiar because you guys basically did this for one of your questions, I think number 2 on the midterm exam. We could also aggregate over a number of DERs. So sometimes, controlling one DER is interesting, but other times we might have 100 or 1,000 of them in sort of a fleet. And we're interested in shaping the overall load profile by adding up all of those different devices. So aggregating here just sort of means adding up over devices. Okay, so suppose we have devices 1 through n. Each of them is consuming power P, or if it's negative, Pi would be power sent back out to the grid. So we add all of that up, and maybe we add in some power from uncontrolled devices as well. So that might be, things in 1,000 buildings that you can't control, all the stoves and blow dryers and whatever else. Okay, then this thing, the aggregate thing, is again affine and non-decreasing in the P functions. And that tells us that sort of the overall properties of the objective function are preserved. They basically are the same for the aggregate power as they would be for the individual powers. And then, so by aggregate, I mean add up over time. And by cumulative, by aggregate, I mean add up over devices. And by cumulative, I mean add up over time. So basically integrate over time. So if we have some objective, some linear objective, say energy cost at a certain hour, maybe we want to add that up over the course of a whole day or a week or a month in order to get sort of the bill, the dollar amount that we'd have to pay. And sometimes when we do that accumulation over time, we use what's called discounting. So you might say, look, a dollar is worth $1 right now, but a future dollar is maybe worth a little bit less to me because I could take the dollar today and I could invest it and turn it into $1.07 a year from now in the stock market or something. So for that reason, you might discount future money a little bit relative to money that happens today. So here, gamma would be a discount factor. If it's equal to 1, there's no discounting. This whole thing would just go away. In general, it might be less than 1, in which case you weight sort of near-term costs more heavily than far future costs. And it turns out that you can do this accumulation over time, and basically you get back an affine function of the power trajectory. So here we'd be looking ahead from time step 0 out through maybe k could be hundreds or something like that. And we're adding it up, and there's a gamma weighted by the number of time steps ahead. And so basically we can write P then as a vector, and then A as well we can write as a vector, which has the time step as well as all the sort of discount factors in there and the prices. And so this thing again is a linear function. So it has the same sort of properties that we've been discussing. So that is a bunch of linear functions of the power. There are also nonlinear functions of the power, and we need to be slightly more careful with these. We need to pay attention to the sort of monotonicity properties as well as curvature. One of them would be energy cost with what's called reduced net metering, or net metering 2.0 or 3.0 or something like this. We've talked about this in the context of California, where California has very high electricity prices, also really good solar resources. So photovoltaic rooftop solar panels are really attractive, or historically were really attractive in California. And the way that that worked in the early days was if you put solar on your roof, your meter would basically just run backwards during the times when you were producing electricity rather than consuming it. And so there was kind of a one-to-one ratio between the electricity that you exported to the grid and the electricity that you imported to your building. So in that case, there would just be one price, and it would be the same whether you are producing down here or consuming up here. And then some states, not all, but many states have moved, especially the kind of states where there's been more solar adoption, like Hawaii, California, Nevada, Arizona, and so on. Many of those states have moved to a reduced net metering scheme where rather than paying the full retail price of electricity, which in California might be like 35 or 40 cents a kilowatt hour, rather than paying that full price for the solar that's generated midday, they might pay significantly less. So it might be 5 or 10 cents a kilowatt hour rather than, say, 35 or 40. Okay, so then here, net demand, this basically is that term P that shows up in our power function. So this would be what we're using in the building minus what we're supplying locally from solar. And so here we're consuming, down here we're producing, and there would be different prices in general. This thing is not linear. It's a piecewise linear function. It's kind of, has an absolute value sort of thing where it has a kink in the middle, right? But it is a convex function. As long as the price that we sell at is lower than the price that we buy at, which is basically always the case. So it's convex and it is non-decreasing. This is actually an increasing function. And here's how we would write it. We can write it as the maximum of these two lines. So this is pi b, slope pi b line, and this is a line with slope pi s, and they both go through the origin. So if we just take the bigger of those two lines, we get this function here, and that is our energy cost. Yes?
So if supply is higher than demand, can you conclude that you're going to basically double profit? Or
Yeah, so if supply from solar, say, is bigger than demand from the building, you're asking, does the utility profit in that case? And the answer basically is no. Not only do they not profit because they're no longer selling you electricity, but actually they pay you, right? That you are now producing, and they are becoming a consumer, not from the wholesale market, but actually from the edge of the grid, from retail customers, right?
at this point of profiting, and in this case is that they should sell more when the demand is higher than the supply, so they can basically offset the amount that they're basically selling.
Yeah, so for a utility to profit in this sort of setting, if they're having to pay you money during these periods, they basically would love it if your demand was big during other periods, right? So that they wouldn't have to pay you as much. You wouldn't be in this regime as much, but also over here you'd be further to the right, I guess. Yeah, so utility would love to sell you more power, basically. Yeah, yes.
Is it possible that residential solar owners could ever essentially like unionize and say, okay, if we're gonna produce X amount of, energy, we should be treated as a generator like that you would normally buy from. You should pay us the clearing price on our kilowatt hours of energy. Like, is that foreseeable thing?
So the question, sorry to, I'll imperfectly paraphrase it, but is what if you had a bunch of people who all had solar on their buildings? Not necessarily all homeowners, they could be schools or I don't know, whatever. And they all got together and said, we want to pool our net load, which could be negative if they're producing, and then they want to appear to the grid like a power plant. Could they do that? Yes, absolutely. And that idea is basically called a virtual power plant. And I think that we will do kind of a read and discuss class about VPPs, virtual power plants. Yeah. I think the barrier is not really technical.
Yeah.
We sort of understand how to do it physically, but it's more laws and prices and markets and things like that. But good question, yes. Okay, so another nonlinear objective is what we might call symmetric demand flexibility. So in some markets, if you want to get paid for your flexibility, they might separately pay you for the ability to like absorb more energy, to use more power, versus the ability to curtail power, to use less. Last I checked, there were some markets, and one of them is the biggest market, PJM, the Pennsylvania, Jersey, Maryland interconnection. where rather than separately dealing with those, the sort of up flexibility and the down flexibility, they want you to submit an offer related to your symmetric flexibility. So they say, I just want a plus or minus number. You can do plus or minus 100 kilowatts. Okay, cool. I know that I can ramp you up or ramp you down by that amount. And so here, to get the symmetric demand flexibility, basically we take the minimum of your ability to move upward and your ability to move downward. So here, this would be the up flex is the blue, and the down flex would be the orange. And you take the smaller of the two, which in this case is the blue. And so then we get this thing here, which is the symmetric demand flexibility. And this thing, it turns out, is a concave function of the power P. Okay. Yes.
So they're gonna assume you're gonna always need at least that much power, the P high bar minus, or PK minus the P top. Like, is that the idea?
So the idea here is that, so maybe we're looking forward over the course of a day, and we're participating in what's called the day ahead, say, wholesale market. So, every day or maybe between noon and 4 p.m., something like that, the grid operator would run a big optimization, and they say, okay, everybody tell me how much power you can produce or how much you're going to need to consume or how much flexibility you have if you're a battery or something like that. They put it all together and they solve a big optimization problem looking ahead over kind of a one-day horizon. And so here, in that setting, P would be like, I might call it like your nominal or your baseline power consumption. So you'd say, look, if you don't tell me to wiggle upwards or wiggle downwards, what I'm going to use by default is just this thing P. But you might want to change that operating point so that you hold sort of more flexibility. So if you moved P down, for example, then you'd have more ability to move up to absorb excess power in the grid when that's needed. So yeah, this would be like P max here would be some physical limitation probably, either set by what your equipment can do or maybe set by like, I don't know, how uncomfortable you can make people in a building or something like that, right? Anyway, so, and then P would be the nominal thing. And then in real time, your actual power consumption might be like in the middle or might be down here or something like that. And so what is this used for? So why do grid operators pay people to be able to provide this service? So one thing this is used for is what's called frequency regulation. So nominally, we'd like to keep the grid humming along at 60 hertz alternating current, which means if you look at the voltage waveform or the current waveform, you measure it on the grid, it's doing 60 cycles per second in roughly a sine wave, right? In Europe and Asia, it's typically 50 hertz, but US 60. So if supply and demand are perfectly in balance, then that frequency stays at 60. But if supply and demand go out of balance a little bit, so say you have less supply than demand, then the frequency on the grid would begin to sag a little bit. And so it might go down to 59.9 rather than 60. And if it sags too far, then you have rotating machines that are basically synchronized to that 60 hertz frequency that that basically for their own protection of equipment would begin to trip off. And that's actually how cascading power outages sometimes can happen, is frequency sags a little bit due to undersupply. And then a generator for safety reasons says, oh, I can't handle this and trips offline. Now your supply is even lower and your frequency sags even more. And then other trip offs kind of tend to happen. So for this reason, power grid operators typically maintain some flexibility that can quickly ramp up. So this might be a gas generator or a hydro turbine, something like that, that can quickly produce more power if it detects undersupply. And actually, it may use what's called automated generation or automatic generation control, AGC, where it's just monitoring the frequency on the grid. And automatically, if it locally measures 59.9, it just increases power production a little bit, something like that. But you could also do that with demand. So you could, rather than increasing the supply from a hydro turbine, you could just decrease the consumption from a bunch of air conditioners, and it would have the same effect. Sorry, that was a very long explanation of a short question, but yeah. Okay, cool. All right, peak demand is another very, very common objective that something like a commercial building like the one that we're in might face from a utility. So a lot of commercial and industrial customers, typically not residential, but the others, typically on their monthly electricity bill, they will have a flat rate, a flat charge, just whatever you use, it doesn't matter, you're always going to pay some $100 a month. Then there would be an energy-based, what's called a volumetric charge, that would say, okay, based on your usage, we charge you based on that. And then or your energy usage. And then there would also be a peak demand charge, which basically says, forget the integral of your power curve. Just show me the maximum value of your power curve. And then they would charge you $1 per kilowatt price, maybe $30, $40, $50 per kilowatt, based on that. And the idea here, again, as I said here, is that demand peaks really are the drivers behind how big the infrastructure needs to be to serve a customer. So how fat the wires need to be, what the transformers need to be rated to cover, stuff like that. And so if you have a higher peak, well, that typically means we need more infrastructure. And so this is basically a way to try to reflect the costs that utilities face in the prices that they show to customers. Yeah.
Only the fleet that's important, or also all around they have been in that.
It's a good question. So is it only the peak, or is it how long you're sort of in those peaking conditions? And the reality is it is not only the peak. So if we only cared about peak, you would be agnostic to whether you have this demand profile or one that actually just tracked this dashed black line forever, that stayed up there at the sort of worst case peak value for the whole day. In reality, one of those would degrade equipment more than the other, right? Because the degradation that happens typically to power lines and transformers is thermal degradation, meaning they get too hot. So transformers are a bunch of wires packed in oil with dielectric material in between. If they get hotter and hotter, all that stuff heats up and you get more wear and tear, more degradation of those materials. And that's what eventually leads to a transformer failing, which can fail catastrophically, can blow up, or they can just say, look, we need to replace this thing. It's too old, too hot. So in reality, you don't only care about the peak. So the peak demand charge is really kind of an imperfect stand-in or proxy for the thing that we really care about, which is how big and new the infrastructure needs to be to serve. That makes sense? Okay, I'm going to wrap up in just a minute here and we'll finish this up next week. But okay, so peak demand price basically, or charge, we would just look at this waveform, typically not over a day, but typically over like a 1 month billing period. And you would look at the highest value. So take the max of this thing and then charge a price, $1 per kW price on that. And so this thing here, as long as this price is positive, this is a convex and non-decreasing function of P. And so this is actually pretty nice. It's easy for us to pack into a convex optimization problem. And yeah, this price range might be kind of on the order of $10 to $50 per kW for a monthly peak. And then you can kind of convert that to a daily price value. Something that you might also encounter. So if you're trying to optimize over, say, a 1 month utility bill, usually we don't have things like weather forecasts or occupant behavior forecasts that we can look ahead for a whole month in a planning problem. We might only look ahead a day or a couple of days. So you might say, look, I don't really care about the peak over the next 24 hours if I know next week there's going to be a super duper hot day and my peak on that day is going to be way higher than the peak today. So you might set what's called a target demand limit. And that might come, for example, you might say, well, last year in May, I paid, my peak was 110 kilowatts. So I would like to decrease that somewhat. So I will set a target, a goal of bringing it down to 100 or to 90. And then you might say, all I'm going to penalize is the excess by which the peak goes above that target demand limit. And so you might have a limit L, and then you have the max here. And so this puts another max basically in the objective function here. So we take the positive part basically of the excess. So this says that if the max of P, which is the dashed black line, is below L, then this whole thing here would be negative, and the larger of a negative number in zeros is 0. And so we pay nothing, basically. But if the black exceeds the orange here, then we would pay something. So this is a way to basically encode some prior information into this sort of truncated horizon optimization, where we only look ahead maybe a day rather than a month. And this is a convex non-decreasing thing. I think this is probably the last one that I'll talk about, but there's a little bit of a weirdness with peak demand charges, which is, yeah, demand peaks drive the sizing of electricity infrastructure, but it's typically not the month-to-month peak. It's typically something more like a lifetime peak. Like if I'm a utility serving your building, I might be serving you for 20, 30 years on the same infrastructure that I put in. So I don't really care so much what your peak is in the middle of March, a mild kind of swing season, I might only care about like how big were those wires that I had to put in the first place, the one time that I paid for them, which is, you know, based on my estimate of how big your peak would be over the course of many years. So to kind of try to catch that, and then another weirdness is, I guess, that the peak that's happening locally at one building might capture sort of the infrastructure impacts in the wires that serve that one building, but they might not capture, you know, the substation transformer, you know, the big power line that might serve, you know, many neighborhoods in the Lafayette area, as an example. And so there, they kind of care about the peak that's coming not only from your building, but from 100 or 1,000 other buildings that's loading that one piece of infrastructure. So there they might say, well, we know the peak times overall for the community are kind of in this period, the system peak. And so we're not going to penalize your overall peak if it's outside of those hours where, you know, the infrastructure is fine. We don't really care. What we really care about is the loading that you're putting on the infrastructure during this critical time. And so there they might take the maximum only over these hours. And so the orange line here is showing the highest value of the blue curve that we see during this kind of highlighted window here. So, so this is again a convex non-decreasing function of the power P, and you can write it in, you know, CVX or CVX pi if you like, by multiplying a matrix C, which is a diagonal matrix, so it's 0 off the main diagonal, and the element on the diagonal is equal to 1 if that hour that you're looking ahead to is a kind of a critical system peak hour, and 0 otherwise. So this matrix C basically just picks out those elements of the power P for which you're in kind of the critical system peak. So this again is a convex and non-decreasing function. And I will stop there, and we'll talk about what's sometimes called demand response or load curtailment or load reduction. We'll talk about that next week on Tuesday. So any last questions about today's material? Yes.
Just on that last slide.
Mhm.
Slide 25.
Slide 25, yes.
Bottom about emergency load reduction
Hmm.
programs. What? So that's like when load gets super high, they'll throw the price way up, or is that?
Yes. Sorry, I'll just go through this whole slide, I guess, because it answers your question there. So apologies, guys, I'll keep you a minute over. But yeah, so for the load reduction problem, we have kind of a baseline profile, which is the orange here. And then we have the true measured power consumption, which is the blue here. And then there might be a window. So like, yes, in California, for example, there's a ton of solar in California. When the sun begins to go down, all that solar drops off the grid, and then other resources have to ramp up really quickly in order to basically keep meeting demand during that time. And so that might be batteries, it might be gas power plants, it might be hydropower, things like that. But basically wholesale prices tend to go crazy during those periods because there aren't that many resources that can ramp up super quickly, okay? So yeah, during those periods, the state of California has this emergency load reduction program, and there they basically raise the price of electricity. Well, no, they provide an incentive, a very high incentive, for people basically to reduce their energy consumption during those periods. So if you can wiggle around your actual power consumption such that during this critical window, it is below your baseline power consumption, you basically get paid for the difference, the area between the orange and the blue curves. And the reason I'm citing this California example is I think this was due to power outages, I think last year, maybe 2 ago. Governor Newsom in California basically said, we need to juice up this program to really encourage people to not use power during these peak times. And so to turn off air conditioners and things like that, turn down air conditioners maybe. So $2 per kilowatt hour is the amount that they would pay you for basically the area between these two curves. So that is, you know, like a 5x increase from California energy prices, which are already among the highest in the nation. So that's quite high. Okay, so I will stop there. Did that address your question?
Yes.
Okay, cool. All right, thank you all. Have a good weekend, and I'll see you on Tuesday.